The subject pertains to troubleshooting power surges in a single-family home with a 200 amps overhead service, feeding two 100 amps sub-panels with a dedicated transformer. The homeowner reported frequent power surges, evidenced by numerous failed surge suppressors and damaged appliances. Initial inspections, including checking connections in the panels, meter socket, and service point, revealed no apparent issues. Voltage readings were normal, and the main panel's surge protection appeared functional. The well pump was identified as a potential source of the surges due to shoddy wiring and poor grounding. Here are some possible causes and troubleshooting steps. Firstly, consider the possibility of a loose neutral. While the panels were inspected, a loose neutral could exist elsewhere, such as in the well wiring or at the service point. Secondly, inadequate grounding of the well pump can create voltage imbalances that may lead to surges. Thirdly, despite the power company's claims, there could still be a problem with the power lines feeding the transformer that causes voltage fluctuations. Fourthly, if heavy machinery or other equipment is nearby, it could induce voltage spikes into the electrical system. Fifthly, although the main panel has surge protection, it's possible it's malfunctioning or not designed to handle the severity of the surges. To troubleshoot, 1. Temporarily disconnect the well pump and observe if the power surges persist. If they stop, it could indicate a grounding issue with the well. 2. Contact the power company and have them re-inspect the transformer and the power lines leading to it. Ask them to measure the voltage and check for imbalances. 3. Connect a voltage monitor to a representative circuit and record voltage fluctuations over time. This can help identify if the surges are originating from the power supply or within the house. 4. Verify if the surge protection in the main panel is still functional. Replace it if necessary. 5. Check the grounding system throughout the house, including the well pump and the service point. Ensure all connections are tight and that the grounding electrode is properly installed. 6. Investigate potential sources of electromagnetic interference in the vicinity of the house and take measures to mitigate it if possible. The fact that the surges are occurring randomly suggests they are not caused by a specific appliance or circuit. The number of fried surge suppressors indicates the surges are significant and need to be resolved promptly. If the surges persist after isolating the well and checking the power company transformer, it's recommended to bring in an electrician to conduct further troubleshooting and identify the root cause. When addressing a loose neutral, it's crucial to understand its impact on a 120 volt/240 volt single-phase system. In such a system, the neutral wire serves as the return path for current from both 120 volts legs. A loose neutral connection can disrupt this balance, causing voltage fluctuations and potentially damaging appliances. For instance, if the neutral connection becomes loose, the voltage on one leg might rise significantly while the voltage on the other leg drops. This imbalance can lead to appliances connected to the higher voltage leg receiving excessive voltage, resulting in damage or failure. Therefore, a thorough inspection of the neutral connections at the service entrance, distribution panels, and individual outlets is essential to rule out this possibility. Pay close attention to the connections of the meter socket, as these are often exposed to weather and corrosion, which can weaken the connections over time. Ensure that all connections are clean, tight, and properly torqued according to the manufacturer's specifications. When investigating the well pump as a potential source of surges, consider the pump starting characteristics and its grounding system. Well pumps typically draw a significant amount of current when starting, which can cause a temporary voltage drop in the electrical system. If the pump's wiring is undersized or the connections are loose, this voltage drop can be more pronounced, potentially affecting other appliances in the house. Additionally, a poorly grounded well pump can create a path for stray currents to flow through the grounding system, leading to voltage imbalances and surges. Verify that the well pump is properly grounded to a dedicated grounding electrode and that all grounding connections are tight and corrosion-free. The grounding electrode conductor should be sized according to the National Electrical Code, NEC, Table 250.66, based on the size of the service entrance conductors. Furthermore, consider the possibility of transient voltage surges generated by the well pump's motor. These surges can be caused by the rapid switching of the motor's windings and can propagate through the electrical system, potentially damaging sensitive electronic equipment. Installing a surge suppressor specifically designed for motor applications at the well pump's disconnect switch can help mitigate these transient voltage surges. When dealing with the power company, it's important to communicate clearly and provide them with as much information as possible about the power surge problem. Explain the symptoms, such as the frequency and severity of the surges, as well as any patterns or correlations you've observed. Request that they perform a thorough inspection of the transformer and the power lines leading to it, paying particular attention to the neutral connections. Ask them to measure the voltage at the transformer and at the service entrance to check for imbalances or voltage fluctuations. If possible, provide them with voltage recordings or screenshots from a voltage monitor to demonstrate the severity of the problem. If the power company is unable to identify the source of the surges, consider requesting a second opinion from a different technician or supervisor. In addition to the above-mentioned troubleshooting steps, consider the following additional measures. 1. Install a whole-house surge protector at the service entrance to provide comprehensive surge protection for the entire electrical system. This surge protector should be rated to handle the maximum surge current expected in the area and should be properly grounded to the grounding electrode system. 2. Use a power quality analyzer to monitor the voltage, current, and harmonics in the electrical system. This can help identify any underlying power quality issues that may be contributing to the surges. 3. Inspect the electrical panel for any signs of damage or overheating, such as burned or discolored wires, loose connections, or cracked insulation. Repair or replace any damaged components as necessary. 4. Ensure that all electrical work is performed by a qualified and licensed electrician and that it complies with all applicable electrical codes and regulations. 5. Educate the homeowner about the importance of surge protection and the potential risks of power surges. Encourage them to unplug sensitive electronic equipment during thunderstorms or other periods of high electrical activity. 6. Keep a detailed record of all troubleshooting steps taken, as well as any findings or observations. This can be helpful for future reference and can also be provided to the power company or other professionals involved in the investigation. When assessing the grounding system, several key aspects should be considered to ensure its effectiveness in mitigating voltage surges and protecting against electrical hazards. Firstly, the grounding electrode system should consist of a properly installed grounding electrode, such as a ground rod, ground plate, or underground metallic water pipe that is in direct contact with the earth. The grounding electrode should be installed in accordance with NEC section 250.52 and should have a resistance to ground of 25 ohms or less, as verified by a ground resistance tester. Secondly, the grounding electrode conductor, which connects the grounding electrode to the service equipment, should be sized according to NEC table 250.66, based on the size of the service entrance conductors. The grounding electrode conductor should be securely connected to the grounding electrode in the service equipment using approved connectors and should be protected from physical damage. Thirdly, the equipment grounding conductors, which connect the non-current carrying metal parts of electrical equipment to the grounding system, should be sized according to NEC table 250.122, based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductors should be securely connected to the equipment and the grounding bus in the electrical panel using approved connectors and should be installed in the same raceway or cable as the circuit conductors. Fourthly, all metallic enclosures, such as electrical panels, junction boxes, and conduit, should be properly bonded together to create a low impedance path for fault current to flow back to the source. Bonding should be accomplished using bonding jumpers, bonding bushings, and other approved methods. Fifthly, the neutral conductor should be bonded to the grounding system at the service entrance only, in accordance with NEC section 250.24. This bonding point provides a reference point for the electrical system and helps to ensure that fault current will flow back to the source, tripping the overcurrent protective device into energizing the circuit. When evaluating the surge protection devices, several factors should be taken into account to ensure their effectiveness in protecting against voltage surges. 1. The surge protection device should be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories, UL, or Intertek, et al. To ensure that it meets industry standards for safety and performance. 2. The surge protection device should have a sufficient surge current rating to handle the expected surge currents in the area. The surge current rating is typically expressed in kiloamps, kA, and represents the maximum surge current that the device can withstand without failure. 3. The surge protection device should have a low voltage protection level, volts protection rating, volts PR, which is the maximum voltage that the device will allow to pass through to the protected equipment. The volts protection rating should be as low as possible, while still being compatible with the voltage rating of the protected equipment. 4. The surge protection device should have a fast response time, which is the time it takes for the device to begin clamping the voltage surge. A faster response time provides better protection for sensitive electronic equipment. 5. The surge protection device should be properly installed and grounded in accordance with the manufacturer's instructions and all applicable electrical codes and regulations. The device should be connected to a dedicated circuit breaker and should be grounded to the grounding electrode system. 6. The surge protection device should have a status indicator that provides a visual indication of the device's operating status. The status indicator should be checked periodically to ensure that the device is functioning properly. Electromagnetic interference, ME, can be a significant source of electrical noise and voltage surges in residential and commercial electrical systems. EMI can be generated by a variety of sources, including radio transmitters, cell phone towers, industrial equipment, and even household appliances. EMI can be conducted through power lines or radiated through the air, and it can interfere with the operation of sensitive electronic equipment, causing malfunctions, data loss, and even permanent damage. To mitigate EMI, several steps can be taken. 1. Identify and eliminate or reduce the sources of EMI. This may involve relocating equipment, installing filters on power lines, or shielding cables and enclosures. 2. Use shielded cables and connectors to minimize the amount of EMI that is conducted through the wiring system. Shielded cables have a layer of conductive material that surrounds the conductors and helps to block EMI. 3. Install EMI filters on power lines to block conducted EMI. EMI filters are designed to attenuate high-frequency noise and prevent it from entering the electrical system. 4. Ground all metallic enclosures and equipment to provide a low-impedance path for EMI to flow back to the source. This helps to reduce the amount of EMI that is radiated through the air. 5. Use surge protection devices to protect against voltage surges caused by EMI. Surge protection devices can clamp voltage surges and prevent them from damaging sensitive electronic equipment. 6. Follow good wiring practices to minimize the amount of EMI that is generated or conducted through the wiring system. This includes keeping wires short and straight, avoiding sharp bends, and separating power and signal cables. When documenting the troubleshooting process, it's essential to maintain a comprehensive record of all observations, measurements, and actions taken. This documentation can be invaluable for future reference, especially if the problem persists or recurs. Here are some key elements to include in the documentation. 1. Date and time of each inspection, measurement, or action. 2. Detailed description of the symptoms observed, including the frequency, severity, and duration of the surges. 3. Voltage measurements taken at various points in the electrical system, including the service entrance, distribution panels, and individual outlets. 4. Grounding system measurements, including the resistance to ground of the grounding electrode and the continuity of the equipment grounding conductors. 5. Condition of all electrical connections, including the tightness, cleanliness, and presence of corrosion. 6. Any repairs or replacements made, including the type of component replaced, the manufacturer, and the part number. 7. Communication with the power company, including the date, time, and name of the contact person, as well as a summary of the conversation. 8. Photographs or videos of any relevant conditions, such as damaged wiring, loose connections, or faulty equipment. 9. Any unusual or unexpected findings, such as the presence of electromagnetic interference or the discovery of a code violation. 10. A summary of the conclusions reached and the recommendations made. In addition to documenting the troubleshooting process, it's also important to communicate effectively with the homeowner. Explain the nature of the problem in clear and simple terms, avoiding technical jargon. Provide regular updates on the progress of the investigation and explain the steps being taken to resolve the issue. Be honest about the limitations of the investigation and the possibility that the problem may not be immediately resolved. Provide the homeowner with a written summary of the findings and recommendations, including any costs associated with the repairs or replacements. Be available to answer any questions the homeowner may have and to address any concerns they may raise. By following these guidelines, you can ensure that the troubleshooting process is thorough, effective, and well documented, and that the homeowner is kept informed and satisfied throughout the process. The material presented provides information for general guidance only. It does not constitute professional engineering advice. Consult with a qualified engineer or electrician for specific applications or situations. Reliance on this information is at your own risk. I am not responsible for any damages or losses resulting from the use of this information.